Okay, so today is just when we're going to go through the review for exam 2 that was posted a couple of days ago, so maybe you've had a chance to look at it. If not, great, we're going to go through all of it today, maybe give you some more practice and examples to refer to when you're studying for exam 2. As a reminder, there is no class tomorrow. Tomorrow is a work day to study for the exam. I will be available tomorrow pretty much via email all day. I won't be around much for video calls, but I will respond to emails as quickly as I can. And then there will also be no class on Friday for exam 2. That will work exactly like exam 1 did. There will be a Canvas assignment that opens midnight Mountain Time on Friday morning and then closes at midnight Mountain Time on Friday night. You'll have the full 24 hours to go in there. And once you go in there, you'll have 90 minutes. I may pad it a little more this time just to give you more time to scan and upload because I know some people were having issues with that. So I may bump it to 95 or 100 minutes, but will be the same kind of deal as last time. Are there any questions on anything? Don't forget to keep up with your ALEKS. I believe there are two different modules due between now and your exam. And then it's okay if you don't get those completely done. The second chance ALEKS assignment will open on Friday as well. So you can go in and get those done over the weekend as well. I also put in your grades for ALEKS modules 1. And if you're confused on what that is just the number of topics you learned before Unit 1 was over. Again, you will get another grade later if you retain mastery of those topics. However, the grades have been put in just for learning your Unit 1 ALEKS modules. And I'm almost done with the homework 2s. I will release those probably like an hour or so after class. Any questions? Cool. Well, if there's no questions, then we'll just hop right into the review. I will share my screen, not the computer screen, the iPad screen. How? Okay, sorry, I broke technology. There we go. Wrong thing. Share screen. Okay. Cool. So you all should have a copy of this document either in YWeb or you printed it out or whatever. I would also recommend that for this, you should have the identity sheet out in your course packet because I'm going to be referring to those a lot. And again, like in a normal lecture, I don't have the actual lecture slide to keep going back and referring to. So I would have that out just to know what I'm talking about when I refer to certain identities. I made the review pretty solution solving equation heavy because we did a lot of proofs yesterday. But just know those are the two main types of problems you'll see on the exam is solving equations and proofs. So with that in mind, let's get into it. All right, first thing we want to do, find all solutions to the equation cotangent of x plus 1 equals cosecant of x on the interval 0 to 2 pi. And we want to write our answer in radians in terms of pi. And basically all that's saying is don't plug it into a calculator and get a decimal for x. We want to actually solve it in terms of pi. Okay. So first thing to do is notice, all right, we're working with a cotangent and a cosecant. Those two things, we can't really combine them. We can't add or subtract them. We can't divide one by the other and get a nice function like sine x over cosine x. We could divide to get a tangent, but we can't do that because these two are weird. So I don't really know what to do. I look at my identity sheet. I want to look for identities that maybe involve cotangent and cosecant to see if there's anything we can do to get rid of them. There's none that involve both cotangent and cosecant, but there's one that involves cotangent squared and cosecant squared. So if we remember, it's totally a legal algebraic thing to square both sides of an equation. So let's do that. Then we may be able to actually work with this. So we're starting with cotangent of x plus 1 is equal to cosecant of x. Then we can square both sides of the equation. 1 squared is equal to cosecant x squared. When we do that squaring on the left-hand side, remember, we can't just do cotangent squared x plus 1. That's not how that works. We actually have to FOIL, in quotes, it out or distribute it out. So we get cotangent squared of x plus 2 cotangent of x. Because remember, we have a cotangent of x times 1 and a 1 times cotangent of x. and then plus 1 is equal to cosecant squared of x. Cool. All right, now I do have an identity that relates cotangent squared of x and cosecant squared of x, i.e. I could turn one of them into the other. Do I want to make the cosecant squared the cotangent squared or cotangent squared the cosecant squared? I think I want to make this cosecant squared into a cotangent squared of some form because I have this middle term 2 cotangent here and I want to be working with only cotangents. So if you look at your identities list, you can see the final Pythagorean identity is 1 plus cotangent squared of theta is equal to cosecant squared of theta. So I'm going to replace the cosecant squared of x I have on the right-hand side of my equation with a 1 plus cotangent squared of x because I can do that by the Pythagorean identity. Let's do that. Then I have cotangent squared of x plus 2 cotangent of x plus 1 is equal to 1 plus cotangent squared of x. Cool. Now, getting everything onto one side of the equation, I'm going to subtract a cotangent squared of x from both and a 1 from both sides. I'm just left with 2 cotangent of x is equal to 0. Beautiful. Which means that the cotangent of x, just dividing both sides by 2, is equal to 0. Cool. Now I just have to think about which angles in terms of radians have a cotangent of 0. What does that mean? Well, cotangent of x equals 0 equals the cosine over the sine using the quotient identity. So that means sine can be whatever. We don't care what sine is. As long as it's not 0, sine is fine. But the cosine of x must be equal to 0. Our numerator must be equal to 0. So let's draw our unit circle. Where on the unit circle is the x coordinate, i.e. the cosine 0? Well, that's right here and right here. That's pi over 2 and 3 pi over 2. So x is equal to pi over 2 and 3 pi over 2. But remember, that's just in the principal interval. For this particular example, we want all solutions. So notice that pi over 2, and then we walk pi around the circle. We get to 3 pi over 2. We walk pi around the circle. Oopsies. We walk pi around the circle again. We get to 5 pi over 2, 7 pi over 2, 9 pi over 2, etc. So we can just combine these two into one solution that encapsulates all of the solutions. And that is just x equals pi over 2 plus pi k, remembering that k must be an integer. We cannot go around the circle a fractional amount. Questions on this one? The absolute hardest part of solving equations, and I will say this myself, I'll even point out where I messed up in writing this a couple times, is using the identities to get the equation down to something we can work with. And then once we do that, it's just unit circle knowledge. But using the identities is absolutely the most difficult part of these. Oh, my bad. It only did want the interval 0 to 2 pi. Well, I did an extra step. If it asked for all solutions, this is what all solutions looks like. Okay. Wow, I remember my own questions so well. Let's move on to the next one. Okay, so suppose that the cotangent of theta is -2/3, and we know that theta is between pi halves and pi. I want to find the exact values, meaning square roots and pi's, of the sine of theta over 2 and tangent of theta over 2. Well, let's pull apart the information we have and then see what we want to get the information we need, which is that. Okay, so first I know that I have an angle theta that is between pi over 2 and pi. So I know it's over here somewhere. I'll just draw some random angle because this is pi over 2 right here, and this is pi. We know it's over here somewhere. I know that the cotangent is -2/3. Well, the cotangent is the cosine over the sine, which is the x coordinate over the y coordinate. So I know that my x coordinate is 2, my y coordinate is 3, but we're in the second quadrant. So we have a negative x, which means this 2 is negative because we're on the negative portion of the x-axis. Cool. I want sine of theta over 2 and tangent of theta over 2. Well, those seem like I would need my half angle identities because we can use information that we have about theta to get information about theta over 2. Now looking at my identity sheet, I remember that the half angle formula for theta, for the sine of theta over 2, is plus or minus the square root of 1 minus the cosine of theta over 2. Cool. And tangent actually has 3 different formulas, but I kind of like the ones that don't involve a plus or minus out front of a square root because those are kind of nasty. So I'm just going to pick the second one, which is sine of theta over 1 plus cosine theta. Cool. So what information do I need? Well, I'm going to need the cosine of theta and the sine of theta. And to do that, I'm going to need to solve for the rest of this triangle first, or solve for the radius, because I'm going to need that to find both the sine and cosine. To do that, I'll just use the Pythagorean theorem. Let's call that r for now. So -2 squared plus 3 squared equals r squared. So 4 plus 9 is equal to 4 plus 9 equals r squared. So 13 equals r squared, which means that the radius is equal to the square root of 13. Cool, can't simplify that anymore. And we know it's not going to be the negative square root of 13 because we're just looking at a radius. Radii are always positive. So that right there is the square root of 13. And now we have the information we need to solve for the sine of theta and the cosine of theta. So the sine of theta, if we remember, is equal to the y coordinate over the radius. So y coordinate is 3. The radius is square root of 13. But in math, we don't like square roots in our denominator. Those are nasty. We want to get rid of them. So I'm going to multiply both the numerator and the denominator by the square root of 13. And we're left with 3 root 13 over 13. Cool. Now what about my cosine of theta? That is equal to x over r, just using the formula for cosine, which is -2 over root 13. But I want to rationalize this denominator too, just so I have something easier to work with. And I get -2 square root of 13 over 13. Cool. This is a problem you probably would have been able to do in unit 1, just this little part we did already. Now we need to think about exact values for the sine of theta over 2 and the tangent of theta over 2, and in particular do analysis with this plus or minus in front of the sine. So let's just start by plugging in cosine of theta and see what happens. So the sine of theta over 2 is equal to plus or minus square root of 1 minus the cosine of theta was -2 root 13 over 13, all over 2. Simplifying that down, doing a little bit of algebra, we get that that's equal to the plus or minus the square root of, I'm going to change that 1 into a 13 over 13. So it's 13 plus 2 square root of 13 over 13, all over 2 still. All I did was make the 1 a 13 over 13 and then combine the two fractions. I added them together, which this is dividing by 2 equal to plus or minus 13 plus 2 root 13 all over 26. And that is your final answer for this one, except we have to think about real quick, is it plus this or minus this? Well, if you remember, the sign, the plus or minus, the positive or negative sign, is determined by the quadrant that theta over 2 is in. Does theta over 2 have a positive y value? Does theta over 2 have a positive sign? We don't care about theta. We know what quadrant theta is in. We don't care about that. Since we're looking for the sine of theta over 2, we care what quadrant theta over 2 is in, and therefore does it have positive x and or y coordinates. So let's think about it. We know that theta is strictly between pi over 2 and pi, but I want to know about theta over 2. So I'm going to divide all sides of this inequality by 2. So I now know that pi over 4 and pi over 2. So theta is strictly between pi over 4 and pi over 2. What does that look like? Well, If we recall, just draw us a little diagram. Theta is between pi over 2 and pi, so theta is over here somewhere. But pi fourths is right here. Pi over 2 is right there. So we know that theta over 2 is just in that little blob right there, which is entirely contained in quadrant 1. Quadrant 1 has both positive x and y values. So the sine of theta over 2, which is in quadrant 1, has a positive y value and therefore a positive sign. So this square root here is positive. We can get rid of both of those, and that is your final answer. Questions there? All right, let's do the tangent real quick, just because we can. So the tangent of theta over 2 using the formula we have written down is equal to the sine of theta, which is 3 root 13 over 13 over 1 plus the cosine of theta, which is negative 2 root 13 over 13. Simplifying that denominator for us a little bit, we get 3 square root of 13 over 13 all over 13 minus 2 root 13 over 13, just turning that 1 into a 13 over 13 and then adding them together. And then these two 13s cancel and we're left with 3 root 13 all over 13 minus 2 root 13. 13, there we go. And that's your final answer for tangent. Questions? Again, when you see something like this where it gives you some kind of trigonometric value for a function like negative 2/3, just remember like cotangent is x over y, tangent is y over x, secant is r over x, etc. Just remember how those ratios work. Pull that information apart, draw it in the quadrant it belongs in, probably solve for the remaining value of the triangle you don't have, pick apart the information, and then, okay, what formulas do I have to get to where I need? What information do I need? And then follow through like that. Okay, let's move on to the next one then. I want to find all solutions to this equation on the interval 0 to 2 pi. Write your answers in radians in terms of pi. Okay, so when I was writing the answer key for this review, I actually struggled with this one a bit. Even though I wrote the question, I wrote the review about a week ago, and then I forgot about it, and then I went to do the review yesterday, and actually struggled with this one a bit, and there's a reason why. My first instinct when I saw this was I saw the, hey, I see a 2 theta here and a 2 theta here. So I spent probably a good half an hour trying to work with the double angle identities because I see that 2 theta and that's immediately where my brain goes. However, that never worked out. The sines and cosines never canceled right, and I never got down to something I was actually able to solve. So I struggled with that. And that'll probably happen to you all a lot because there's times where something will look like something and then it won't work and it's frustrating. However, there's another identity that isn't, I don't think is immediately recognizable as the double angle ones, but that definitely works here. If you remember, look at the sum and difference identities. If we look at the sum identity for cosine, in general, we have that the cosine of alpha plus beta is equal to cosine alpha, cosine beta minus sine alpha, sine beta. Cool. This doesn't look like exactly what we have, but we can manipulate it so that it does. So taking my equation 2 cosine 2 theta, cosine theta, minus 2 sine 2 theta, sine theta. I can factor out a 2 from both terms, not from the inside. I can't touch this 2 inside the theta, but I have a 2 here and a 2 here, so I can factor those out. So that's just equal to 2 cosine 2 theta, cosine theta, minus sine 2 theta, sine theta. Cool. Now, what if we say, looking at the general form of our equation up here and this, if we say that alpha is equal to 2 theta and beta is equal to theta, does this work? It does. We have cosine of alpha, cosine of beta, minus sine of alpha, sine of beta. So it turns out we actually can use the sum and difference identity to do this one, even though my gut instinct just from looking at this was, hey, this is probably a double angle identity equation. It's not. This is what we would use a sum and difference identity for, which will work out really nice, and we'll see why in a minute. So using that sum and difference identity, we can reduce all of this mess down to just cosine of alpha plus beta. So let's do that. So we now know that 2 times the cosine alpha, which is 2 theta, plus beta, which is theta, is equal to -1, just the -1 from up here. Simplifying this down a little bit, 2 cosine of 3 theta is equal to -1. So the cosine of 3 theta is equal to -1/2. Now, we can't really do anything with the 3 theta. There's no magic formula that fixes the 3 theta. However, if we remember, this is the point where we don't even need any trig identities. We would just do a little substitution. For now, let's set a equal to 3 theta. So now, instead of solving cosine of 3 theta equals -1/2, we're just solving cosine of some angle A is equal to -1/2. In other words, we want to look at what angles A on the unit circle have an x-coordinate of -1/2. Well, those happen right here and right here. This is about x equals -1/2. So it is these two angles here. Drawing the unit circle, help me remember that, oh, these angles are 2 pi thirds and 4 pi thirds. Cool. Now we have the solutions for A in the principal interval. Even though we will only want the solutions in the principal interval for theta, we still need to write the general equations for A because we need to make a table of solutions to find all the solutions for theta. And we'll see what that looks like in a second, but we have done this before. So in general, our two solutions for A are A equals 2 pi thirds plus 2 pi k, and A equals 4 pi thirds plus 2 pi k. At this point, we want to now resubstitute theta back in for A so we can solve for theta. Doing that, we get that 3 theta is equal to 2 pi thirds plus 2 pi k, and dividing everything out by 3, we get that theta is equal to 2 pi ninths, because 3 divided by 3 times 3 down there is 9, plus 2 pi thirds k. Similarly with the other equation, we have that 3 theta is equal to 4 pi thirds plus 2 pi k. Therefore, theta is equal to 4 pi ninths plus 2 pi thirds k. Cool. These describe all of the solutions for theta, but we don't want all the solutions. We actually just want the solutions on the principal interval. So let's build a table and use these two equations we've constructed to solve for all of our possible solutions just between 0 and 2 pi. So set up our table here. First equation we're going to look at is 2 pi ninths plus 2 pi thirds k, which is the same as 6 pi ninths k, just making a common denominator. And then 4 pi ninths plus 6 pi ninths k. Cool. When k is 0, we have the solutions 2 pi ninths and 4 pi ninths, because we're not adding anything to those principal solutions. When k is 1, we add a 6 pi ninths k to both of those, and we get 8 pi ninths and 10 pi ninths. Cool. Those are both still less than 2 pi, because 2 pi is 18 pi ninths, so we're still good to go. Let's do another one. K equals 2, we have the solutions 14 pi ninths and 16 pi ninths. Both of those are still less than 2 pi. So let's do another one. we now have 20 pi ninths and 22 pi ninths. These are both actually greater than 2 pi, so they are not on the interval 0 to 2 pi. So when you are listing your final set of solutions within that interval, you would not list those two. But we know that these 6 are in the interval 0 to 2 pi and are solutions. So this particular equation has 6 solutions in the principal interval. Questions on this one? Again, a lot of the ones I gave you on the review are very involved, just to try to get you to practice all of your skills. Not all of the ones on the exam will be this involved, I promise, but it's good practice just to remember, hey, can I solve this right away? If the answer is no, what trig identities could I apply to it? And if they don't work out for some reason, trust your algebra, trust that it's not you doing something wrong, that maybe it's just not the correct formula to use, and look at your identity sheet and try something else. Okay, let's move on to another one. I want to find all solutions to the equation 2 minus 2 cosine squared of x equals 2 sine squared of x over 2. Okay, so what should I do for this one? I can't really solve it right off the bat. And even though this looks like a Pythagorean identity problem because I have a cosine squared and a sine squared, I can't use the Pythagorean identity because I have this pesky x over 2 in here. So I need to get rid of that. And pretty much when you see an x over 2, the only way you're going to nicely be able to get rid of those is using half angle identities. So that's what I'll try to do first. It seems like the intuitive thing to do. And if it doesn't work out, we'll try something else. Okay. So we're starting with 2 minus 2 cosine squared of x is equal to 2 sine squared of x over 2. Before I use the half angle identity, I noticed that if I divide literally everything by 2, I can just factor a 2 out of this entire thing to make it nicer to begin with. So I'm going to do that. And we're left with 1 minus cosine squared of x is equal to sine squared of x over 2. I like that a bit more. Just get rid of the 2's. Okay. Using the half angle identity for sine of x over 2, I'm just going to substitute that in right here. So we now have 1 minus cosine squared of x is equal to plus or minus the square root of 1 minus cosine of x over 2 squared. I already like where this is going because now we're working just in terms of cosines. We don't have to deal with any nasty sines. Those are gone. We only have cosines. It looks a bit disgusting on the right-hand side, but that's going to go away pretty quickly. So remember, when I square a square root, that square root goes away, as does this pesky plus or minus in front, which is really nice because regardless of whether this was the positive or negative version of this, when we square it, we're going to get the same thing. So we don't even need to regard the plus or minus anymore. That will go away when we square it. So let's do that. We now have 1 minus cosine. 1 minus cosine squared of x is equal to 1 minus the cosine of x over 2. I'm going to multiply both sides by 2 just to get this pesky 2 out of my denominator, which leaves me with 2 minus 2 cosine squared x is equal to 1 minus cosine x. And then just getting everything over to one side of the equation. I'm solving 2 cosine squared x minus cosine x minus 1 is equal to 0. I can solve this. This is a quadratic. I can factor this. I could either use the quadratic formula just to get me straight to the roots, or I could put it into factored form using the AC method, which factored form for this is just 2 cosine x plus 1 times cosine x minus 1, just thinking about what multiplies to get us to AC and adds to get us to B. We would end up with this. Now, cool, I have 2 factors. If I didn't use the quadratic formula, which I didn't, I now need to solve for the roots of this. So I have that 2 cosine of x plus 1 equals 0, and I want to set cosine of x minus 1 equal to 0 as well. So Solving these, I get 2 cosine x, subtracting a 1 from both sides is equal to -1, which means that cosine of x equals -1/2. I now want to consider what angles on the unit circle have an x coordinate of -1/2. Well, drawing my little unit circle, because pictures always help. I see that those are the angles right here and right here. So my x coordinates here are 2 pi thirds and 4 pi thirds. Cool. It's going to want all of my solutions, so I'll just write out the general form of these now. We need to keep these two separate because they don't skip around the circle in nice intervals. So I have the two general solutions, 2 pi thirds plus 2 pi k, and 4 pi thirds plus 2 pi k. Let's see if I get another solution out of this guy right here. Cosine of x minus 1 equals 0. Adding a 1 to both sides, we just want to solve for when the cosine of x is equal to 1, i.e. which angles on the unit circle have an x coordinate of 1. Well, in the principal interval, there's only one of those. It's right here. So x in the principal interval is equal to 0, which means the general solution for this is just 0 plus 2 pi k. In other words, just pi or 2 pi k. But remember, we need to specify for all of these solutions that k is an integer. Questions on this one? Remember in the last problem, we had some stuff in our argument that wasn't just x, and we ended up having to do a substitution with a. That only worked because the only cosine in the equation, it had a 3 theta in it. There were no other cosine thetas being added, because if we tried to make the substitution that a was equal to 3 theta, it wouldn't have worked. So what I'm trying to say is we couldn't have done any substitution for the x over 2 here. We couldn't have said that a equals x over 2, because then we would have also needed to substitute this x here for 2a, and then we would have been having the same problem just in a different way. So the only time we can do a substitution like that is when the argument of all of the trig functions is the same. If we have a 3 theta in every single trig function. If we don't, it's not going to work very well, and that is when we should try to use our double and half angle identities to instead get rid of the x over 2 or the 2 theta in the argument. This was one of those cases when that worked very nicely. All right, let's take a break from equations for a minute and let's do a couple proofs. I want to prove this identity here. I want to prove that 1 plus sine x over cosine x plus the reciprocal of that, cosine of x plus 1 over sine x, is just 2 secant of x. I'm looking at this. I think I want to start with the left-hand side of the equation, because the right-hand side, although I could do something with it, I could use the reciprocal identities to floop that secant into a cosine. I don't really want to do that yet because I can't really go anywhere once I have that. So not really a point of starting in the bottom. So I think I want to start with the top because it's the most complicated. So I have 1 plus the sine of x over cosine of x plus cosine of x over 1 plus sine of x. I know at the end, this is going to end up being quite possibly a 1 over cosine of theta, which is just one fraction. So I want to take these two fractions and combine them into one. I can't add them yet because they don't have a common denominator, but I can make them have a common denominator by multiplying this entire fraction by 1 plus sine x, and this entire fraction by cosine x over cosine x. So let's do that. Let's make our common denominator. So we have 1 plus sine of x times 1 plus sine of x all over cosine of x times 1 plus sine of x. Notice, oopsies. Notice all I did was multiply by the fancy 1 here of 1 plus sine of x over 1 plus sine of x, just to make a common denominator with this one, which is going to be cosine of x times cosine of x over cosine of x times 1 plus sine of x. Cool. Now these two have a common denominator. We can add the two fractions together. So doing that, and in the same step, I'm going to do this distribution up here. I have 1 plus 2 sine of x plus sine squared of x plus cosine x times cosine x is cosine squared of x all over cosine of x times 1 plus sine of x. Still no trig identities used, just doing algebra to get this into one equation. Okay, but I now have it into one equation, and I might want to think about, okay, what trig identities could I use for this now? Well, I can actually use my favorite one. Sine squared plus cosine squared, the one we know and love, that's the Pythagorean identity. Sine squared of x plus cosine squared of x is just 1. So we now know that is 1 plus 2 sine of x plus just 1 all over cosine of x times 1 plus sine of x. And I have to label, how did I get to this step? I used the Pythagorean identity. Cool. Just adding those two things in the numerator. It is 2 plus 2 sine of x all over cosine of x times 1 plus the sine of x. Factoring 2 out of the numerator because I can, I'm left with 2 times 1 plus the sine of x over cosine of x times 1 plus sine x. Notice I have this common multiplicative factor of 1 plus sine x in both the numerator and the denominator. So those cancel out, and I'm left with 2 over cosine x. Still no other trig identities used here. However, this is the same pretty much as 2 times 1 over cosine x. And we know that 1 over the cosine of x is just the secant of x. So this is just 2 times the secant of x, which is what we wanted. I got here by using the reciprocal identity on this last step. And the proof is done. Questions on this one? Again, good rule of thumb, if you don't know what proof identities you could use, or if you don't see any that you could use, just try poking it with your algebra toolbox, seeing what you can do, seeing how you can squish it around, make things look different. And then maybe something like this will pop out that you're like, aha, I recognize that. And then you can try trig identities. All right, let's do another proof real quick. I want to prove that the cotangent of x times 1 minus cosine of 2x is equal to the sine of 2x. Cool. So this one I could honestly start on either one. I could start on the left or the right-hand side. However, I think I'm actually, even though it's a lot simpler, going to start on the right-hand side this time. And the reason for that is because the sine of x only has one double angle identity. There's only one thing that the sine of 2x could equal. However, the cosine of 2x could equal 3 different things. And I don't really know which one it's going to be yet. So I kind of just want to write down my first step to see where I'm headed, and then maybe try to use that to figure out which cosine double angle identity to use. So at the end, I know this is going to equal the sine of 2x. And using my double angle identity, the sine of 2x is equal to 2 times the sine of x times the cosine of x. Okay, so all that told me is in the end, I'm going to need a sine and a cosine in there. Cool. That's not that much information, but it'll help guide when I decide what to do with the double angle identity for cosine. So now let's go back and just start at the beginning. Now that we have this thing that we're aiming for down here, I know that the cotangent of x times 1 minus cosine 2x. I'm not going to touch that cosine yet. because I know my answer is going to be in terms of only sines and cosines, and I see a much easier way to start getting it into sines and cosines. We can turn cotangent into sines and cosines. So just using the quotient identity, cotangent of x is equal to cosine of x over sine of x, and then times 1 minus cosine 2x. And to do that, I use the quotient identity. Okay, now I'm really out of stuff to do and I have a choice to make. Which of my 3 cosine double angle identities am I going to use? Well, I know I'm going to want 1 cosine and 1 sine in my answer. I already have 1 cosine here in my numerator. I think that might be the cosine I end up with in the end, but I don't know yet. But I also have this pesky sine in the denominator. I not only need to cancel out because it's in the denominator, I need another one in my numerator in order to get a sine x and a cosine in the numerator when I'm done. Looking at my sheet, one of the double angle identities for cosine is 1 minus 2 sine squared. I think that one would work. That would not add any extra cosines to my numerator. It wouldn't, and it would cancel the sines. So let's try the one that just has sines in it. So this is equal to cosine of x over sine of x times 1 minus 2 sine squared of x. This one might not work, but let's try it. And I know this was a double angle identity. Cool. Simplifying that down a little bit, cosine of x over sine of x times 1 minus 1, the 2 1s go away. Perfect. That works out nicely because we're not going to want that 1 there in our final answer anyways. We're just left with a negative distributed to a negative as a positive, 2 sine squared of x. Rewriting this out, it's 2 sine squared of x times the cosine of x over the sine of x. This actually worked out perfectly. What we see happens here is this square will cancel with that sign down there because we have a common multiplicative sign in both the numerator and denominator, which we'll just leave with the 2 sine x cosine x, which is the sine of 2x. Reading this forwards, we know we had to use a double angle identity here. And this is actually done. So let's just go back and look at what happened here, because it is kind of weird sometimes when the 2 parts of the proof meet in the middle and it's like, oh, did I actually finish? We did. So all we did in the first step, turn that cotangent into a cosine over sine. Then we cleverly picked which double angle identity for the cosine of 2x we were going to use. There were 3 we could have tried. Again, if you didn't pick the correct one the first time, you can always go back and try again. There's only 3 of them, so maximum, it should only take you 3 tries. And then just simplifying it down, we notice that, hey, 2 sine x cosine x is precisely the sine of 2x using the double angle identity. And that's all that was really done for this one. Sometimes it helps to work backwards, meet in the middle a little bit. If that's not how you think, that's okay. You can just work it forward all the way through, whatever's best. Questions on this one? Okay. I had a little typo on this one. Find all solutions to the equation tangent of 2 theta over 3. I wanted to say that it's equal to -1. You can't have an equation without an equal sign. I don't know what happened to it on that one. My apologies, but we want to solve the equation tangent of 2 theta thirds equals -1 on the interval 0 to pi. I don't really know how to address that 2 theta over 3 in my argument, so I'm going to do a substitution. I'm going to set alpha equal to 2 theta thirds and deal with that later. I don't want to look at it. I would much rather just solve the equation. Tangent of alpha is equal to -1. That's much nicer. I can do that. So when is the tangent of alpha equal to -1? Well, that usually happens the only time when the sine and cosine are equal, which is what we need for the tangent to be plus or minus 1 in the first place, is when the sine of alpha over the cosine of alpha is in some form root 2 over 2 over root 2 over 2. That is the only place on our unit circle where the sine and cosine are equivalent. So since tangent is negative, though, we're looking for -1. What quadrant does that occur in? Well, remember that occurs in the quadrants where we have opposite signs for x and y. So that occurs in quadrants 2 and 4. So we're looking for the angles that have sines and cosines of root 2 over 2 in those two quadrants. That happens right here and right here. These angles are 3 pi fourths and 7 pi fourths. Cool. Now, again, we only want solutions for theta on the interval 0 to 2 pi. However, because we did a substitution, we're going to need the general form of the solutions for alpha. Just so we can get all those solutions. We're only going to need one equation here because we're jumping around the unit circle in increments of pi. So alpha in general is equal to 3 pi fourths plus pi k. And k is an integer. Questions on this yet? All right, now that we have this, let's substitute 2 theta thirds back in for alpha, solve for theta, and then fill out our little table. So because alpha is equal to 2 theta thirds, we also know that 2 theta thirds is equal to 3 pi fourths plus pi k. Multiplying both sides of the equation by 3, we get that 2 theta is equal to 9 pi fourths plus pi k, or not pi k, 3 pi k. And dividing both sides by 2, theta is equal to 9 pi eighths plus 3 pi over 2k. So this equation right here describes all of the solutions for theta. However, we only want the ones in the principal interval, so we need to use that equation, trying different values of k to solve for the solutions on that interval. Making our little table. We know that theta is 9 pi eighths plus 12 pi over 8k, just making a common denominator. And k is 0. We have 9 pi eighths. And k is 1. We have 9 pi eighths plus 12 pi eighths, which is 21 pi eighths. Okay. Normally I'd keep going, but notice 2 pi is equal to 16 pi eighths. 21 pi eighths is already bigger than that. So our only solution in the principal interval here is theta is equal to 9 pi eighths. So this equation, even though we're used to the ones with the substitution having many more solutions, this one actually only has one solution. This one has less solutions in the principal interval than alpha did. Questions here? All right, let's solve one more equation and then there are a couple more proofs and then we are done for today. So the equation I want to solve is sine of 2x plus 2 cosine of x equals 0 on the interval 0 to 2 pi. Now, this one is actually not too bad at all. It'll be a little weird feeling, but it's not bad, and we'll see why. Can't really do anything here, 2 cosine x, whatever. But I have the sine of 2x, so my gut immediately says, I want to use a double angle identity. So I'm going to try that, see what happens. There's only one double angle identity for sine, so I'm going to use that one. So using that identity, I get that 2 times the sine of x times the cosine of x plus 2 cosine of x equals 0. That's just the double angle identity for sine. That's all I did there. All right. Notice that in both terms, I have a common 2. What's up, Charles?
when you have the question that says just find all solutions rather than prove, do you want us to label what we do there or not? What do you prefer?
That's a good question. I will let you know on the exam in each question exactly what is required. I will probably have you label in some cases, especially when there is going to be one that's identity heavy, but I will let you know exactly what I expect.
Okay. All right. Thank you.
Cool. Yeah, thanks for reminding me of that because that's a good question. Okay. So notice that within each of these terms I'm adding, I have not only just a common 2, but also a common cosine of x. So I can factor those out. I'm still in terms of sines and cosines, can't really do anything about that, but I can factor something out. So doing that, I have 2 times the cosine of x times sine of x plus 1 equals 0. Now, this may look a bit uncomfortable because we still have an equation in terms of both sines and cosines. However, it's in factored form. I can very much set both of these factors equal to 0 and solve them individually. This is a legal way to solve it. Normally, we want to turn all of the equations into the same trig function so that we can solve it much nicer. But because we have it in factored form, it's totally mathematically legal to say, okay, I have this thing in factored form. I want to solve for when 2 cosine of x equals 0 and when sine of x plus 1 equals 0. Because I can do those 2 things separately. I technically kind of have 2 distinct equations here. This one only involves cosines, this one only involves sines. So we're actually good to solve this one this way, even without changing the cosines into sines or vice versa. And that's because we were able to factor it. So let's solve this. Solve the one on the left first. We are looking for where the cosine of x equals 0, i.e. where on the unit circle, what angles on the unit circle have an x coordinate of 0, not the unit oval, the unit circle. Thank you. This happens here and here. So these 2 angles are x equals pi over 2 and 3 pi over 2. Now let's solve the one on the right. We're looking for where the sine of x equals -1, i.e. what angles on the unit circle have a y coordinate, because we're looking at sine now, of -1. Well, that happens right here. We already have that as a solution. Technically, the only solution to this factor is 3 pi over 2. So our solutions overlap, which is a bit uncomfy, but that means that these are the 2 solutions. And the reason they overlap like that is because we have factors, one factors in terms of sine, one factors in terms of cosine. It's technically legal. We have all of the solutions, and that's just pi over 2 and 3 pi over 2. Those are the 2 things that we could plug in for x to the left-hand side of the equation to make it equal to 0. Questions on this one? All right, let's take a breather for a minute, do one that is hopefully fairly easy. Let's use a cofunction identity to write an expression equivalent to the cotangent of 63 degrees. Well, if we remember, in general, the cofunction identities are function of x equals cofunction of pi over 2 minus x. So all we need to do, we know that the cotangent of 63 degrees, well, what's the cofunction of cotangent? It's tangent. And then pi over 2, how many degrees is pi over 2? Pi over 2 is right here on the unit circle. How many degrees is that? Converting it to degrees, that's 90 degrees minus x, which we said to be 63 degrees. So this is just the tangent of 27 degrees. And that's all you need to do for this one. If you ever see something like this, you would use a cofunction identity. It just means apply the cofunction identity using its correct cofunction and do the pi over 2 minus whatever your x right here is, and that's all. Just being able to write cotangent of 63 degrees with an equivalent expression in terms of tangent instead of cotangent. That's all. Questions? All right, we have 2 more proofs and then we're going to be done for the day. Just a little more practice with these. I want to prove that 1 plus the sine of negative x over 1 plus the cosecant of negative x is equal to the negative sine of x. I don't really want to start on the right-hand side. There's nothing I see that I could do there. Again, if I was really, really smart, I'm sure I could expand that into looking like the left-hand side somehow, but I'm not that smart. So I'm going to start with the easier side. So I'm going to do 1 plus the sine of negative x over 1 plus the cosecant of negative x. Right away, I don't like these negative signs in the argument for either sine or cosecant, but I know that both sine and cosecant are odd functions, meaning that I can pull that negative from the argument out to the front of the trig function. So this is equivalent to 1 minus the sine of x all over 1 minus the cosecant of x. And this was by the even odd identities. Cool. Now what? Well, I don't really like that cosecant in my denominator. I know my final answer is just going to be in terms of sine, and I know that the reciprocal of cosecant is sine, so I can get it in terms of all sines just right now. So I'm going to do that. So this is equal to 1 minus sine of x, leaving my numerator alone. And then it's equal to 1 minus 1 over sine of x. This was by the reciprocal identity. Okay, now I'm going to have to use a bit of cleverness here, and it's cleverness we actually saw yesterday. So I have something like this in the denominator, but I don't want anything in my denominator. I want to cancel this out somehow. I want just a negative sine of x in my numerator. So I'm going to try to factor that out of my numerator. It doesn't look like I can right now, but just to be a little bit clever, I know that 1 is equal to sine x over the sine of x. So I'm going to rewrite the 1 in the numerator like that just for now, and we'll see why in a second. I did it like that. So now it's a little more apparent that I can pull a sine of x out from both terms. I can pull this sine of x out from the numerator, and I can pull that sine of x out there. So what that's going to look like is I want a negative sine x as my final answer. So I'm going to see what happens when I pull out a negative sine of x. When I do that, the sine of x gets pulled out from there, and I'm left with a negative 1 over sine of x. And when I pull a negative sine of x out of here, I'm just left with plus 1. Notice that this now and this cancel out. Why is that? Well, I have 1 minus 1 over sine of x. Those are the exact same factor. They're just in a different order. So they actually just cancel out, which is beautiful. And we are left with exactly what we were trying to do, which is a negative sine of x. This was the bit of clever weirdness with factoring that we saw yesterday, where we said, okay, my final answer is just a negative sine of x. There's nothing in my denominator. How can I pull this factor out of my numerator so I can just completely cancel the denominator? And that took a bit of cleverness. It doesn't look like we can factor out a sine of x from the number 1 because there's not a sine of x in the number 1. But if we rewrite it like this and get our brain starting to think about, there is technically a hidden sine of x we could pull out of there, it would just leave us with a 1 over sine of x, then maybe, just maybe, I can get it to look like the denominator. And the fact that there's a 1 over sine of x in the denominator as well should be a tip off that that's the correct move to make. Any questions? Again, there are probably other ways to do this. You could multiply by a fancy 1 of sine of x over sine of x at this stage to get rid of the fraction in the denominator, if that's what's making you uncomfortable, and then try to factor out a sine x, that might be easier, but it is completely up to you and whatever feels most comfortable for you when you're doing these, because there is never just one correct way to work through these. That is unfortunately how math works. When you get to a point of doing proofs, there is almost never one right way to do something, which is both a blessing and a curse. All right. On that note, let's try one more. I want to prove that the cosine of 3 pi over 2 minus x over the cosine of pi plus x is equal to the tangent of x. I think we can all agree that the left-hand side is probably the best to start on here, because I immediately see that I could use sum and difference identities and some evaluation in order to just cancel stuff out, and then we can see what we're left with and go from there. So cosine of 3 pi halves minus x all over cosine of pi minus x. Looking at my identity sheet, I'm going to use the difference identity for cosine on both the numerator and denominator to expand those out a bit and get cosine of 3 pi, that's a 3 pi halves, cosine x plus sine 3 pi halves, sine x all over cosine pi cosine x minus or plus, is it? No, it's a minus because down here it's a plus sign. I wrote it incorrectly. Minus sine pi sine of x. And this was by sum slash difference identities. Cool. Now I notice I can do simplification by evaluating these 4 guys right here. So I'm going to do that. Equals the cosine of 3 pi over 2. I'm just going to draw my little unit circle down here because it helps sometimes. Cosine of 3 pi over 2 is the x coordinate of this right here. So that's 0 times cosine of x. Plus the sine of 3 pi over 2 is the y coordinate of that angle right there. And that's -1 times sine of x. All over cosine of pi is the x coordinate of this right here. So that's -1 times cosine of x minus the y coordinate of pi, which is 0 times sine of x. And this was just by evaluation. All I did was evaluate trig functions. Cool. Now multiplying those things by 0 and getting rid of them, I'm just left with negative sine of x over negative cosine of x. Negative divided by a negative, they cancel each other out. So this is just sine of x over cosine of x. And I'm being a little bit verbose here. This is like, these aren't steps I would need to write out. I'm just being explicitly clear in what I'm doing. But recall sine of x over cosine of x is just the tangent of x. And that is by the quotient identity. And we are done. This one was pretty straightforward, just trying the one logical identity that made sense. And then once we evaluated everything correctly on the unit circle, the answers kind of fell out nicely for us, which it's fun when that happens. It's nice when math just works out how we want it to. Questions on anything from the review at all? Again, if you are still stuck or would like to do more examples, ALEKS is a great resource. It's pretty much just an unlimited pool of different randomized questions to keep trying, and that offers explanations if you're confused on what to do. So ALEKS is great. I will be here as a resource. You can email me whenever, and I will get back to you quickly if you want help or you want to do an example, whatever. But yeah, this is the entirety of the review. Remember, no class tomorrow. It's a work day. Finish the homework by midnight tomorrow. Review for the exam, make your note card, do what you need to do. Again, the 2 things I would focus on that would get you probably 95% of the content from this unit are solving trigonometric equations and proving identities. Those are the 2 main things to focus on. That was pretty much the entirety of the content from this unit. But yeah, that's all I have for today. Let me know if you have any questions. Otherwise, have a wonderful Wednesday, and I will see you all next week, next Monday. Wow. All right. Have a good day.